Hi, everyone. Yep, I'm Emma, much shorter introduction. Currently in Nottingham, travelled not far from London before that, but always in cosmology, always in first stars since I began my career at UCL years ago. And tonight I thought I would talk about something fairly relevant in the news, which is the James Webb Space Telescope a little bit, but mostly why it's been capturing everybody's imagination in terms of, well, the sensationalist headlines we've had. No, I'm going to use this anyway. Excuse me. No, I'm just sorry. Okay, right. I might just do that. We'll see. But anyway, so this is the James Webb Space Telescope. How many of you have seen it launch? Did any of you watch it launch? Yeah. How many of you did it live? Oh, friends.
So there's something wrong with the screen. The screen share right now. Look.
Okay, well, you do that. Well, is it okay if I just carry whittering on? Okay. Okay, so I mean, it was a very special moment for me. I don't know about how you, but I have 3 small children, and they all had to stop what they were doing at about 12:30 on Christmas Day, surrounded by presents. I was like, no, anything noisy with batteries, get out. Mummy needs to watch this. And I honestly wept just a little bit when it did go up, and that's because it has been over a decade of watching the James Webb Space Telescope being conceived as a project before my time, but during my time actually being built very slowly all around the world, but mostly within the and honestly, a lot of us were holding our breath because it was so full of untested technology that are you okay? Do you need me to...
I am sorry.
What is wrong with it? Is it the double vision?
I think I have figured it out. I just need to get the presentation to. Where's this?
Okay, well. All right. Anyway, what's the thing? JWST, lovely. Yes, untested technology. So for example, the sun shields here, they stretch out these big aluminium-esque foil things. They are about the area of a tennis court, and they have to fold out this tiny little package because all of this had to fit on the bottom. Indeed, the actual mirror itself is this here. That was 3 segments basically, which folded up like that in the rocket, and it had to fold out like that, which I saw a fantastic Halloween costume last week of somebody who had a section on each arm and was just the folding JWST. Amazing. Legend. Anyway, and so over the last decade, people very secure within the collaboration have been reassuring the wider astronomy world that this was definitely going to work. Definitely going to work because it's been tested before. Wink, nudge. And so all we knew that it was probably military technology that had been tested before, but nobody could actually say it or tell us why it was going to be okay. But everyone was willing to believe it. And happily, it did work because it cost $10 billion, which is no small amount, and no small amount to get past Congress either. And it was really quite incredible to have the first results from JWST announced not only by a press release, kind of live webcast, which again is a new thing very much this decade, but also actually by the President of the United States here, who's looking very happy. This lovely image of galaxies, and did any of you watch the press release of the images? Yeah, a few people. Good. Okay, I mean, how many times did we say United States of America in that one little 2-minute segment? It was literally like JWST USA, but it was an international collaboration. Very much ESA was involved. But yeah, let's let them have it, shall we? So it was wonderful that they gave it this kind of press release. It's another argument about whether that was the best image to have released. I'm not quite sure. I think all of us are already immersed in astronomy and all can already kind of say I'll get onto a lovely bigger picture of this later, don't worry. This is incredible. There's lots of different galaxies, but it's more the kind of the Stefans Quintet, which really got me. This is the one where, again, I wept. Like, I cry very easily, apparently, when it comes to astronomical images. But this one came out where you've got the Hubble at roughly the same wavelengths. It's an unfair comparison, really, because Hubble was made for optical, but it could do a limited number of UV infrared wavelengths. And so here we've got the Stefans Quintet in the different wavelengths, and it's absolutely stunning what you can see in the infrared, because JWST utilizes these different wavelengths of light to pierce through the dust that Hubble was having to deal with, that blocks this optical light. And it can go right in there, it can look into the stellar nurseries within these galaxies. It can look into different kinds of things about these galaxies. And just so we're a little bit fairer, that's Hubble in the optical. But what you can hopefully see is that even when you kind of match to the eye resolutions, JWST is actually much more powerful, but to our eye, they're all pretty impressive there. But you can see the kind of different structure. I mean, I find this top right one fascinating here. It just looks like a completely different galaxy to me, in a different wavelength. But for my field, this was the image which really blew us all away. It covers an area on the sky of a grain of sand, held at arm's length. Not that it matters, tiny or tiny, it doesn't really matter, but it is tiny. And so you have to think that all of these structure in here, of which the vast majority are galaxies, not stars or anything like that, is that all of that exists on this tiny grain of sand on the sky. And not only that, but all across the sky in every direction. So it really is enough to cause existential panic attacks in the best of people. And you can see all different kinds of structures in here. You've got the one, I don't think I've got a pointer, but I don't think it really matters. Oh, I do. Okay, so this is the cosmic sausage. Everybody say hello. This is actually what it's called. Unfortunately, if you print a paper on something, you get to name it. And so somebody thought, let's capture some headlines, and sure enough, they did. And this is the cosmic sausage. And the reason it's called that is because it's slightly elongated, but there we go. And the reason it is as you can see with all of these as well, you can see lots of what's called lensed galaxies. And what's happened is that this field on the sky, that's what we call the area of the sky that we're staring at very intently, this is imaging what's called a lensing cluster. So it's a huge cluster of galaxies that are so massive that they are warping space-time, bending light, so that galaxies that are in the background are actually being magnified and distorted, just as if you've got a magnifying glass and you're looking at whatever you want to be looking at, clues on the ground in the Sherlock Holmes story, whatever. It's distorted, it's moved. And so this is what you can kind of see here. And you can see all the kind of different colours in here, which we'll get onto soon. But the key thing to take away from this is that we are seeing very old light. So these aren't necessarily old galaxies, because the light that we are seeing in this image has been traveling to us for so long that actually it could be from a very young galaxy. It's just that light is only just getting to us. So these old galaxies, these are, there you go. The old light that we can see in this image is a way that we can kind of look back in time. And we can start to look at these different galaxies and start to find out about our past. So why can we do this? We can do this because light has a finite speed. We're used to it as being very quick, 300 million meters per second. That's pretty fast. So if I wave to you, you see it as your brain perceives it instantaneously, no delay. But there is a delay. So if we're waving at our friend on the moon, for example, or Neil Armstrong, Buzz Aldrin, and Michael Collins when they're landing on Apollo with Apollo 11, there's a 1.3 second communications delay to the moon, which really matters when you're asking somebody to abort a landing. So they have to take this into account. It would take 1.5 seconds-ish for any command to get to them, and 1.5 seconds for it to get back. a 3-second delay. That's the problem. When we're looking at Mars, if we're waving at our friend on Mars, it takes 4 minutes for the signal to get there and 4 minutes for that signal to get back, by which time we're like pretty annoyed because it's been 8 minutes since we've sent a signal and our friend's completely ignoring whoever. And now let's move a little bit further to our nearest galaxy. This time we want to say hi to our friend in Andromeda, let's say. 2.5 million years for any communication signal to get there. 2.5 million years for any communication signal to get back, by which time you're not just very annoyed, you're very dead, right? It's been 5 million years. And so the key thing here is that when we receive a signal from somebody in Andromeda, we are seeing them, we're getting the communication as it was sent 2.5 million years ago. So we are hearing from them, seeing them, understanding them as they were 2.5 million years ago, and vice versa. So if there is a group of researchers in Andromeda right now looking at us, they're not looking at us, they are looking at the earliest ancestors of the human race. This absolute human species, this absolutely blows my mind every time. I'm really sorry, that's me, isn't it? I've just realised me getting overly excited, so I'm going to do this so I don't keep doing that. So it's mind-blowing to me as somebody who grew up wanting to be a historian. I never wanted to be an astrophysicist particularly. It's not something I grew up with. I never belonged to a society like this. I never went to look through a telescope, nothing like that. I wanted to be a historian. I wanted to be an archaeologist. I wanted to be an Egyptologist, anything like that. And in the end, another story, I ended up doing this and finding out about a history that's much, 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 much older than anything that I could find on Earth. I am a historian. I'm a historian who happens to use a telescope. And the history that I'm interested in is from 13 billion years ago, a little bit older than Cleopatra. So light is our key. If we can look at light that has been traveling to us from a very, very long distance away, then we can see that time, that area of the universe as it was in the past. It's time travel. And the way we can understand and kind of like how that light would look, how to tune into it, is what color it is. So there's a concept called redshift. And what's happening to this light is that it's traveling, let's say, 13 billion years, which is the era I'm interested in, the very, very first stars to exist in our universe. That travels to us, that light, and I wouldn't say it loses energy, that's a little bit of an incorrect thing to say, but it works against the expansion of the universe such that you can think of it as going into the longer wavelengths of the spectrum. So we see the light as redder at the kind of lower energy of the electromagnetic spectrum. This is called redshift. So when we're looking at something nice and blue and young, so star-forming galaxies are very hot and white and blue and young. Actually, if we were seeing them as they were 13 billion years ago, yeah, they might be blue back then, but that light's been traveling to us for so long that we would be seeing it as red. And that's why, if I got it, yeah. No. That's why when I said about this with the different colors, is that we can kind of take a quick look at this and say, that's very red, that must be pretty old, and that one's pretty red, and that one's pretty red, and kind of be like, wow, we found loads of old stuff. And indeed, that's what happened over August and July. So astronomers like me were really excited in July and like weeping when these first images came out. And then the scientific community kind of leapt on them, understandably so, because we've been waiting for so long and spent $10 billion on it. That a whole raft of papers came out on our public repository saying, we've discovered a galaxy which is only 200 million years from the Big Bang, light from this galaxy as it was only 200 million years after the Big Bang, 300 million years, 400 million years. Every day it seemed like there was a new paper, to the point where at one point a friend said, have you seen this new paper? And I actually just asked them to shut up because I couldn't take another one. I didn't have time to read one more paper from this damn telescope, which was working way better than anybody thought it would. And the first way that they were doing this was quite seriously by looking at the image, having a look at where your reddest light was, what it looked like in the different wavelengths, and finding what we call candidate galaxies. So it's kind of your cursory look. This produced a huge number of papers. Very exciting. It's very exciting because JWST has always had the planned ability to push back right to the very early stages of star formation in our galaxy. So these are all the kind of the flagship experiments, and you've got JWST, which is they've not quite updated the slide on the website. It still says future, but it's there, and it is planning. We were planning for it to go all the way back to about 200 million years in our best dreams. After a while, once we'd got to grips with the telescope, what actually happened was they turned on the telescope on Friday night, went to sleep, woke up for breakfast on the Saturday morning and had that deep field image that I showed you. There was not a huge amount of post work in it. There's a lot of pre-prep in terms of making the telescope, but in terms of getting that image, they got something that would have taken 2 solid weeks with Hubble, for example. And then they found these candidate galaxies of possibly 200 million years after the Big Bang. For it to do that within the first 12 hours of a however many year mission is absolutely astonishing and actually quite petrifying in terms of what we might end up finding, because the volume of data that's going to come from this is going to keep you all in jobs for a really, really, really long time. So that's good for you. You end up going down this route. Why do we care? I don't really have to fill this question in too much for a group like this, because you all naturally care about the skies for some reason. The reason I care is because I do consider myself a historian a lot of the time, and not knowing something about the past, whether it's how the pyramids were built or how life began on Earth, or what started the first stars, like why did the first stars happen? You have this Big Bang. We've got lots of evidence for that. I'm not going to go into that, take it my word for it. We've got lots of evidence that the universe began in this big, energetic, explosive Big Bang. So explosive that you couldn't form full objects. You couldn't have stars and galaxies popping out of the Big Bang. And yet here we are. So something in between happened. And actually up until July, when JWST launched, or struck first light, we didn't have many observations. In fact, we had one very contentious result, which I might have time to talk about, within the first billion years of our Big Bang, of our universe. So we've got the Big Bang, we've got evidence for that called from the background radiation. That's about 380,000 years after the Big Bang. And then pretty much in terms of observations, we've got nothing until about light from about 1 billion years after the Big Bang. That's, if you're looking at a human lifetime compared to the lifetime of our universe so far, that's missing everything in your life from the day you were born to the first day you went to school. All of that information gone. Now, that's a huge amount of data to be missing. And so as a scientist, even if you don't care kind of like from a historian point of view of like just wanting to know and having understanding a narrative, from a scientific point of view, if you're missing that much data, you are almost certainly going to be making incorrect conclusions, even about matters in the modern day. So one of the key ones we trot out is supermassive black holes. So supermassive black holes are at the center of most spiral galaxies, including our own, and they're too big. They're way too big. They're far, far, far too big for how long the universe has been around and how much they could have been accreting or eating up all this matter that they're managing to attract towards them. They shouldn't have grown that big. Nobody can really explain that, except if we go back into the era of the first stars, we switch on a telescope, we look back in time and we see the baby black holes. And that's one of the things that we're trying to do with the experiments that I'm coming up to talk about in a minute, but not JWST. So the other reason just put this up and realize I'm in the chemistry building, aren't I? Okay, so this is the periodic table of elements, according to a chemist. Lots and lots of them. And actually, I walked past the cabinet just out there, which is full of lots of different, very, very posh elements. I call them posh elements because as astronomers, this is what we have. And that's because after the Big Bang, you get two. You get hydrogen and helium. It makes your exams a lot better. You get a smidgen of lithium. Basically, this is no joke. We call everything metals. So we call all of the stars like high metallicity stars. And by that, we mean it's got stuff in other than helium. That's it. So the interest of this is that somehow you get from a universe which has just got hydrogen and helium in it straight after the Big Bang, to a universe like today, where a carbon-based life form can breathe oxygen and wear silver and all of these very posh elements. Where did they come from? Well, the answer is the first stars, and indeed every other star after that, but it was the first stars that really began this kind of factory process of processing the universe. So these stars, what they're doing all around us today, but especially these first ones, is they are taking in the raw materials of hydrogen and helium. They are fusing them in this very energetic process. And then when they die, they supernova, they explode eventually, then they are polluting, they are populating the surrounding universe with all of those heavier elements, all of those metals. They all throw them out into the local environment. But it's these first stars which are what we call metal free, and that's because they are just hydrogen and helium. So this is kind of the other big reason that I would say it's important to know about them, is because they are responsible for the biggest chemical change in our universe, and they did that in a way that you can't recreate around us today. So you cannot make a new metal-free star anywhere in the universe, because it's so polluted with metals instantly after these first stars die that you can't form them again. You are instantly stuck with forming metal-poor stars or metal-rich stars like our sun. So you just have this endless process. So last reason to care is the first stars are very strange. So because of the I'll ad-lib. So the first stars of the first weeks, I think it's just at 8 o'clock, we might just decide to turn it off. Okay, well, I mean, I can still talk to you, that's fine. So the first stars are very strange in themselves, because whereas you could, for example, should we call something like the sun normal, which it's not really, it's a little bit small to be an average star, but let's call it normal. Compared to the sun, the first stars were about 100 times the mass of the sun, if not up to 1,000 times. There's some simulations which should forecast them to be up to 1,000 times the mass of the sun, which is astonishingly massive. And actually so massive that there are theories which say that a star that massive just actually can't exist, or rather it exists for such a fleeting moment that it almost instantaneously collapses into a black hole. So it's almost like there is no star stage, it's straight into a black hole. And actually it's that which could explain supermassive black holes, is if you can jumpstart the process of creating a black hole by just not having the star form, because it's so massive, it just crushes down that fast. That could explain it. So the first stars are very massive. The reason they are this is for reasons I'm not going to go into detail, but chemistry. So if when you want to cool something down and collapse it down, you have to get rid of all the heat. So you push something together, even like a bike tire or anything like that. You really, really apply pressure, it's going to get hotter. You need to get rid of that heat somehow. If you've not got access to heavier elements, it's very hard to do that. So in the early universe, you can't collapse a gas cloud down as efficiently. It doesn't fracture like they do now and form lots of little stars. In the early universe, what would have happened would there have been maybe one or two humongous, massive stars, 100 times the mass of the sun. there may be a little fragmentation into some tiny, tiny sibling stars. You can ask me about later about why that's interesting if you want, or if there's an awkward silence, that's where I'm going to go. So the big implication as well for why I can't just show you a picture of a first star, instead have to rely on very nice PowerPoint artistic effects, is that we haven't ever seen a metal-free star. We have not been able to observe one. And that's because they're all dead, or are they? For sibling stars, we'll come to that later. But the chances are the vast majority of these first stars are dead, if not all of them. And that's because they were so massive, they fused through their fuel so fast that they were dead within 1 million years. It's been 13 billion. They're long, 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 long gone. So how are we going to see? How are we going to find out about this time? Well, excuse to show another JWST image. This is, oh my God, I've forgotten what they called it now. What is it? The cosmic cliffs, that was it. The cosmic cliffs, not a great name. So this is a big kind of big cloud of dust and star formation going on here. And you'd think that we'd be able to, for example, just use JWST. It can look really far back. We might be able to tune into the light from this era. The problem is that even for JWST, going back to that really, really first star, first galaxy era is really tricky, because it's so far back that the lights, like the peak, the most of the light has been redshifted out of even JWST's visual spectrum. So, you know, it's gone into the infrared and past it into what we will find out in a minute are the wonderful radio wavelengths, which is where I work. So we're not able, even with JWST, to kind of pick out the very first times. And more than that is that even if we can see one of the very first galaxies, like we supposedly have seen with JWST, or one of the first few million years, 100 million years of a galaxy, it's still a sample of 1 or 2 or 3. It's not a larger scale on the sky like other surveys can give. It's a very concentrated survey. So the aim is what can we do to go back even further? And the work that I do is not directly with JWST, though I use the results, but I use radio. Now, I warn you, the reason I put lots of pretty pictures about JWST is because radio can be a little bit underwhelming to the untrained eye. So here we've got a composite image where you've got one galaxy in lots of different wavelengths. And what I'm trying to convince you of is that this one's the best one, which might be a hard sell. But what I hope I can definitely sell you on is that the different wavelengths tell you different things about the universe. So the big one to really notice here, the one that radio is most famous for, is the jets. So these huge jets of radio light can be seen from loads and loads of different galaxies. And in optical, you wouldn't have a clue. You'd think it's just a normal boring spiral, loads of dust, lovely. You switch on the radio and suddenly you've got these massive jets, which, as you absolutely should, define them as part of the galaxy. Your galaxy suddenly gets much larger in how you perceive it. And these jets are thought to come from central black holes. And so it's almost like a sign saying black hole here, where in optical, nada, you can't see anything. So with radio, yes, it might look a little bit overwhelming, but you have a signpost, you have a way of diagnosing something different about your universe. This is just another one. This is I forget what galaxy this is actually. No. Anyway, and so again, you can see lots of different kinds of wavelengths here, and it's the radio where you can really pick out kind of different features that you just can't see in the near infrared. What that's telling you is about what the processes are that are going on. You can tell that, for example, there's a synchrotron radiation happening, therefore there must be this kind of magnetic field, or etc. Lots of different kinds of things. I love radio. I didn't always. I ended up doing a PhD in astrophysics, thinking that I'd be going to Hawaii. and or Chile and Tenerife, and going to all these optical telescopes. And I was told that my telescope would basically be in the Netherlands, which is very flat and rainy. I was quite disappointed, but actually over the years, I have absolutely fallen in love with them, and now make it a thing that anywhere I go where there's a nearby radio telescope, I end up driving to have a nerdy picture taken with it, because I find it incredible that these kind of contraptions, which look completely useless, like they look like something that Sky TV threw out of the back of their truck, to be honest, you can tune them in to see light further than JWST. That's mad. So this is this year. This is what I've been up to on my holidays since Easter. So this is Jodrell Bank in Manchester. Please go, even if it's like a 2-hour drive at a weekend, just do it. It's incredible. Their visitor centre is second to none. This one, I was visiting Berkeley, and I saw it on the hill. And I said to somebody, I was like, what is this? And it turns out it's tracking NASA lunar missions, which I found really interesting. So that they let me go up there and watch it. And then this one is in California. It's 4.5 hours drive north of San Francisco. And this one is a fun one, because it's the first dedicated array for the search for extraterrestrial intelligence. And I could not miss that one. So I went up there into the wilderness, the alpine forest, where there was snow on the ground in May in California. And there were 4 scientists who live there permanently, and they have lived there since before COVID, bless them. Like, they were not planning on being there that long. But honestly, there is nothing anywhere near, like there's not even a shop. They have to do a 4-hour drive every few weeks to get food. And they are very odd, but amazing. Like, don't quote me. So, they're really nice. But what's interesting about them, that I'm going to caveat that with, is that they're very odd in the way that they've had to live isolated for several years. 4 years. And they've had to, one of them I interviewed for something, and they actually watched the wildfires last year. That were very serious wildfires. They watched them on the ridge, and they all abandoned, and there was one left. This guy, Viel, he was stood there with a suitcase packed, watching these wildfires with the array of servers behind him going, please no, please no, please no, please no. Because he's like, I'm not going. And apparently he's just like, oh, sod this, I'm not going down the ship. But luckily the next morning they start to back off. But the reason that I do want to caveat it is that that SETI array is actually one of the most advanced pieces of technology I've ever seen on Earth. It's funded by billionaires. So the SETI initiative has not got a good reputation because people like me put silly gifts like that of aliens, but actually it is the most incredible technology because they've been underfunded for decades, because they've not been taken seriously, despite what is a very serious question, which is anyone out there? Can we listen? We can use radio for that. It's a very simple thing to do in a way. What this array does is they look at a list of 200 stars, and they look for radio signals from those solar systems, and they look for 5 minutes, and then they move on, and they do that for years and years and years, just in case they missed a call. It's funded by billionaires. It's absolutely fascinating, so do always take it seriously. And I better hurry up now, but this is Arecibo. So this was the last one I went to see in July, and this is 0.3 kilometers in diameter, which this is why I love radio. You try building that and launching it on a rocket. Like, this is why radio is down to earth, is because we get our I just had something, you just mentioned that I was wearing the boots of a geologist. This is because as a radio astronomer, I walk through deserts and jungles in order to use the radio telescopes. And so I'm very used to having waterproof, sandproof boots on, and I wear them all the time. And this one is incredible because the larger the dish, and this includes JWST, the higher resolution, the better sensitivity you have for a telescope. So when you've got a 0.3 kilometer dish, until it falls, until that big thing falls on it a few years ago, very sad video if you watch YouTube, it can listen in incredible, exquisite detail and build up some beautiful, beautiful images. So you can build really, really big dishes. What's even more fun with radio is that because you're playing with such long wavelengths of light, that you can think of the light as seeing a smooth surface, even if there's really large gaps. So you're quite familiar with this whenever you make a jacket potato or whatever you're doing, is that you might have never noticed or really processed the fact that your microwave always has this kind of semi-opaque view. Like, why can I not see my jacket potato? Why? And the reason, of course, is because you want to be able to see it to make sure your porridge isn't overloading or something like that. So your optical light needs to be coming through, but you do not want to be cooked in the process. And so for microwaves, what you need to do is you need to put what looks like a mirror to microwaves. Now, microwaves have a longer wavelength than optical light, so they see a surface as being a mirror, even if it's got these tiny, tiny gaps. And so for the microwaves, it just bounces right back off, straight back into your potato. And it's the same thing, same idea that we use for radio telescopes. So this is the underside of Arecibo. So that massive dish that I just showed you, you could get on a 4x4 and drive under it. And it's got its own ecosystem under there. It's absolutely, including a pink orchid that only grows under the dish of Arecibo, which is absolutely astonishing. Anyway, what you can see is it's made of chicken mesh, basically, chicken wire. It's just made of mesh. That's all it is. And yeah, this is serious technology. But what we can do is we can make even bigger gaps than that mesh. And this is what I do. So this was several years ago now. This is my baby. This is the one in the Netherlands that I work with all the time, called LOFAR. And what we've done is we've got 1,300 of these little guys, bow tie antennas, and we've placed them all over Western Europe, making what is in effect a radio telescope the size of Western Europe. And for 10 years now, since 2011, we have been tuning in to the exact color of light, the exact wavelength of radio light that we know we're getting a signal from that time, from 13 billion years ago. And so we've been listening very hard, trying to find this detection. And it's been one heck of a race. There's lots of people doing it in a very good-natured, competitive way. And we haven't found anything yet. We will. But the reason it's so hard is because we're looking for a signal from this time that is extremely faint. It's been traveling for 13 billion years. And anything at that same kind of wavelength that arrives to our telescope at the same wavelength is going to be, we're going to see it. It's all going to get junked together. So it's like trying to listen to the radio and having a pirate radio station overlay it, except that our pirate radio station is our galaxy, and it's about 10,000 times louder, which is really, really loud. And so my day job is looking at statistical methods to remove all of that and denoising, get to that signal. We're getting closer and closer and closer and closer and closer. How long have I got left? Oh, really? Nice, captive audience. Cool. Okay, yay. In this case, it's unusual I get time to talk about this, but so the one kind of contentious result that I spoke about earlier that has come in this time so far is from an experiment called EDGES. And even I don't remember what this is, an experiment to detect the global EOR signature, which has in itself an acronym, which is the epoch of reionization. Horrible name, for which I don't think I've got a slide. Yeah, I'm going to do something slightly unconventional and just skip forward very quickly. Yeah, okay, so I just want to explain the acronym really. What I want you to imagine is that we've got 3 different eras of our universe here. So here is our first era. This is about 100 million, well, straight after the Big Bang, about 380,000 years after the Big Bang. Everything started settling down. Universe has become transparent and light. Everything's traveling normally, expanding and cooling. And if you just looked at all the hydrogen in the universe, that's what we look at with our radio telescope. So we talked about underwhelming. This is the kind of data that we're looking for, because what we tune LOFAR and other experiments into is the wavelength of light emitted by hydrogen. In the early universe, there's a ton of it. If you took a big photo of it, it'd just be completely saturated, loads of this. Then you'd go on and you'd have your first stars forming. Now, these first stars, they throw out so much what we call ionizing radiation is that they separate out this hydrogen into its proton and its electron. So it doesn't produce any light anymore. So we can't actually see it. And so you get bubbles or holes. We call this the Swiss cheese ball, which is when you've got the stars. That's called the cosmic dawn. It's around 200 million years after the Big Bang. Now we step forward into the much longer period of, let's say, from 200 to 1 billion years after a Big Bang. And this is what I just wanted to very quickly go forward to, which is the epoch of reionization. And it's a horrible name for what basically means that you've got enough stuff emitting radiation in your universe, like stars and galaxies, that all of that hydrogen in the universe goes from being what we call neutral, so having its proton and its electron nicely stuck together, to being ionized. So it's all in its constituent parts all over. And if we were to take an image of the neutral hydrogen as a whole around us today, we'd see nothing because it is in a mostly ionized state. So now I've actually explained what that is. We can go back to that. And this is why it's a stupid name. But anyway, edges. This is amazing because we've been taking data for 10 years with all of these different telescopes, including the massive dishes and then the little diddy ones like mine, where we've got, in effect, a massive dish, but made of lots of teeny weeny parts. And this, I got rung by the Guardian saying, we've got a paper that's been embargoed, it's coming out tomorrow, could you comment on it? And they sent me it, and it was the paper from this collaboration, and it was that they had made a detection of the cosmic dawn. And I'm like, I'm sorry, who are these guys? Like, I'd never even heard of them. Or like, they were on my radar, but as kind of like a almost failed experiment, because I've been turning up to conferences and presenting nothing for so many years that we'd all assumed that it had completely failed. What they actually did was they got one single antenna the size of a table, one metal antenna, and they put it down in Western Australia. And instead of, if you can imagine, taking kind of an image of the sky of all that different hydrogen, looking at all these different bubbles, they did something much simpler. They just took the temperature of that hydrogen. And what they said they found was that in the early universe, what you'd expect is that everything's very cold. Well, not in the very early universe, it's very hot, but everything kind of expands and cools down. It keeps cooling down. But then you have the first stars forming. And where there are stars, there is heat, as we know. And so what you would expect to see is that temperature of the hydrogen upticking. You'd start to see it heating a little bit. And it was this effect that they measured in this paper. They said they had measured. And what this did was place a single data point in that lost billion years, which was that the first stars had formed enough to heat that gas by 180 million years after the Big Bang. That was our first single data point, and it still is the only kind of data point from this time. So this was a really shocking result because nobody had seen it coming. And actually, it turned out that they'd known about this for years, but were doing a lot of checks on their data and checking it over and over and over and over again, as they absolutely should with something this odd. Because what they found was they didn't just find a timing of like 180 million years after Big Bang, fine. What they found was that the gas was actually much colder than they expected. And it's difficult to go into this on without a whole other talk. But what they found was basically, yes, it was a bit hotter, but it was a lot colder than all of our models actually predicted. And so this is one of the images, which, I mean, I read this paper and I was just walking around the house like, what the heck? Oh my goodness me, they've done it. This is amazing. I can't believe it. They've done it. And then I get to like page 8 and I'm like, wait, what? I'm like, wait. And I have to reread the whole thing because I'm so confused. And it's because every single model we have, even the so-called exotic models of all these different kind of grey lines here, it didn't fit any of them. So the red line is what they actually measured. It didn't fit any of them. So don't worry about what it is or what shape or what this is telling you. Just have a look at the fact that even our wildest, like, that'd be mad, guesses at what the universe could be doing did not fit the data that was coming from edges. Now, going back to a kind of similar vein and what I started with JWST is that, as is of course what happened, is that the press jumped on it And certain scientists jumped on that. And they said, well, really, the only thing that can really cool down a gas at that time, there's not much going on in the very early universe if you've just got hydrogen, helium, and oh wait, dark matter. So maybe it could be dark matter, which is famously uninteractive. It's very, very difficult to see because, well, we haven't. It can only see it in terms of how it gravitationally interacts with our universe. So for there to be a way that we had indirectly detected the effects of dark matter by looking at the early gas in the universe was absolutely sensational. And that is where all the headlines went. Now, it has only in the last year been increasingly I'm really sad about it actually, but increasingly obvious that actually this is probably not a real result, in that there might be something there 180 million years after the Big Bang in terms of heating, but it might not be that kind of excessive cooling by something like dark matter that maybe we had hoped, because it's exciting. Like, we want something weird to be happening. It's exciting. But I wanted to mention it because it is the same kind of narrative that I wanted to just riff on a little bit in terms of the JWST, in terms of that it's been a really exciting summer in terms of our field and astronomy in general when it's the JWST. But we have to proceed with caution at this time because the results are so new and so unverified. And I'm really being reductive here, but most of the early kind of we've discovered something really old has been it's red. Whereas it's only 2 weeks ago that we've started seeing the first confirmations of those candidates. And happily they are coming in. As I'm not being pessimistic, I'm a very optimistic person. I do think that most of these are going to be fine. But you do have to go in with some skepticism here, because we need to have what happens is JWST says that looks very red, and then they get a team to look at it for a week with a different kind of method or a day or whatever. They get a much more detailed look at the light from this galaxy, and then they can kind of have a look at the actual age of it. And we've had the first couple of confirmations of very, very old things. And so, yeah, and that is a relief, actually. I haven't updated this, but this was kind of the latest thinking on JWST, which was that it's a bit of a panic, really, because a lot of the first papers that came out from these it's red reductive analyses was that actually they had jumped on data that was 12 hours old, and it was publicly released, and that meant that it was released to anybody outside of the JWST collaboration. So anybody like me with some astronomical tools could take this data, do something a little bit not dodgy with it, but to the best of my knowledge, the best that I could possibly do, but that I may have not understood the complexities of that telescope, because calibrating a telescope after only 12 hours, like you've asked the majority of work. And so I was really happy last week to start seeing these first spectroscopic confirmations coming in. And then if I've got a couple of minutes, just one more thing to say, which is that also, that was my super red thing. Yeah, okay. Just to point out that this is what we think is the oldest light from JWST. So we think this is called the cosmic tomato, I think they called it. Anyway, it's the cosmic tomato, and yes, it's light that is so red. This is not one of the spectroscopically confirmed ones, but it is light that is so red that this could be right within that era that I told you about, which is this reionization, this very, very early stages of galaxy formation. And if correct, something's going a little bit odd, because galaxies shouldn't be that fully formed at that time. So again, the most exciting thing that can happen, which is that we can't explain this. This is odd, this is weird, keeps us in the job, but we do have to go forward with a little bit of skepticism. I don't think I've got time for that one, but again, awkward silences. You can ask me about whether Hubble's dead. So this is the future for me, which is with my LOFAR telescope, we are hoping to make what is one of the first detections of the light from the era of the first stars, and we're going to be doing that with this method where we don't look for the individual stars because they're too small, too faint, they're too far away in terms of light travel time for us to get that kind of resolution. What we do instead is we look for the effect on their environment. Just like you can't see that black hole optically within those optical images at that resolution, you turn to the radio, suddenly you can see them. You can see the effect on their environment. We're doing the same thing with the first star. So it may look underwhelming, but that's only because I don't have pretty images and have not spent the time on making these pretty. But using our next generation telescope, which we're building at the minute, called the Square Kilometre Array, we're putting 130,000 of these Christmas tree antennas in the Western Australian desert. There's some very nearby here in a field. If you ever get the chance to go out there, they're testing them there. And the precursor, so like the test array of that, not those Christmas tree antennas, but the other part of the SKA, has already started giving us images like this. This is a false color image, but it's stunning. And this is a radio image. And I like to end on this because I give you lots of kind of like low res stuff, because I'm looking at things 13 billion years ago that haven't been detected yet. So it's a little bit of a hard sell. This is our galaxy in the radio, taken by one of the precursor arrays. And you can see that it is not the Milky Way that you know. It is a different place. You've got these incredible streams. What you've got is runaway pulsars. You've got supernovae bubbles. You've got filaments of cosmic ions like following the magnetic field. It's an astonishing place to live and look at in the radio. So that's about me done. If you, I wrote a book, so if you're interested in the wider area at all, or you want to learn a little bit more about the kind of science behind JWST in terms of what it's actually going to be looking at in terms of the galaxies and things like that, but mostly radio. Yeah, Christmas is coming up. Okay, thank you.
So the first one asks, the JWST image of very early galaxies are mostly seen as red, that is highly redshifted from star forming UV. Why then do we see some blue galaxies? Shouldn't these have redshifted similarly?
Yeah. It's because while that I'm showing and our brains can process a 2D image, what we're seeing is light from a 3D universe. And so we're not just seeing light from the oldest galaxies 13 billion years ago, we're also seeing light from galaxies that are much closer, but the light is arriving to us at the same time. And so it will have been redshifted different amounts. And so you'll be seeing a bluer galaxy that's closer to us, for example. But it's really complex, and this is why we do have to be careful, because, for example, you could have what's called an interloper, which is where, for example, you think you're looking at a really old galaxy because it's very red. It could actually just be a close by galaxy that's really red. And so you have to be very careful, and you have to check the chemical elements and how they've been redshifted to be absolutely certain. And that's the kind of spectroscopic evaluation I was talking about.
Yeah, we have another question along kind of the same lines, but more specifically, how do you know that the radio waves are captured in telescopes are from close to the time of the Big Bang rather than other cosmic objects, maybe even specific wavelengths? Close to our time, how do we close out what's close by and what's far away? Yeah, so this is, I wish I had a whiteboard, but if it's statistics and a little bit of AI these days, in the while they arrive to us at the same wavelength, they are different shapes. So I want you to kind of imagine that if you've ever used a radio, you're tuning your radio by turning the knob to go from like 88 to 92 FM or whatever like that. You're changing the wavelength. Now,
if you do that while you're looking at a signal from the first stars, you can imagine completely different songs happening, really, really crazy dissonance. So you're going from like Katy Perry to, oh, this is put me on the spot, to the Rolling Stones, to Beethoven, to Taylor Swift, and just completely different shots of music, so that you're just like, what is going on? So it's a very what we call dissonant, decoherent signal. Now imagine that you're listening to something much closer by, so like our galaxy, the Milky Way. You're tuning your telescope just exactly the same. So it's just, the radiation's arriving to you at the same time, but suddenly you're hearing one song just at a different volume. So one song, I'm really, oh my God, now I literally can't think of another. Ed Sheeran. You're listening to Ed Sheeran. This is not a reflection on my musical tastes. You're listening to, it's a reflection on my children's. I promise you, maybe apart from Taylor Swift. You're tuning your radio and you hear the same Ed Sheeran song, but at a different volume. And so suddenly, even with your own ears, or rather our eyes, statistically, we can pick these things out. You're like, that looks a little bit rough, whereas that looks really smooth when we look at the different frequencies. And statistically, you feed that to something like machine learning or AI, and it can actually, hopefully, be able to pick it out quite not easily, but there's a possibility, thank God.
Sorry, very interesting talk, thank you. I was curious whether some of the properties of the first stars could be probed with some redshifted form of gamma ray bursts from some near directions.
It's a really good question. Oh, goodness me, gamma ray bursts. So if there is a process where you've got very, 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 very bright gamma ray bursts happening, then there is no reason why it wouldn't be redshifted down so that we could see it at different wavelengths. Now, in terms of whether there would be a process on the resolution, because the issue you have is that you're looking at something that's so far back that you're kind of the area that you're probing is very, very large. You've got lots of galaxies. You're not looking on an individual star level, you're looking on masses of galaxies. And so being able to find a process where that was bright enough, I'm not sure, but yeah, possibly. Gravitational waves is one that is another probe if you're interested in what's called multi-messenger astronomy. So radio is one way, but by far the most promising way is the way I've told you, is the radio waves are going back into this time. It's our best bet. But gravitational waves, there's a possibility that if you have two of these direct collapsed black holes, so these massive black holes that kind of skip the stellar stage, if they collide in the very early universe, they might create a ripple in space-time, which we could pick up with the Future Gravitational Wave Observatory, LISA, which is going to be a space gravitational wave observatory, which when I was, how old was I? 19? I wrote my undergraduate poster on how LISA was going to be done in the next couple of years. And what are we now? I forget my age, but it's a long so yeah, eventually LISA will be another way of looking. I think there's a question. Yeah, hi.
Yeah, you said the first stars were really massive and could possibly collapse directly to a black hole. If they did, how did they pollute the universe with their metals?
So those ones wouldn't have. So exactly that is that if you have polluting a universe with the products of fusion requires it to be expelled in you exploding your layers out. If you have a black hole, whether it's a direct collapse one where you skip the stellar stage, or whether there is a certain number of these first stars which just naturally go into black holes, just like you have a few stars around here that still do that now, you would lose all of those metals. And so that we have to take that into account in our simulations. And if you have those kind, then you lose that and your metallicity will be lower than you think about it. But by tracking the metallicity of the gas, by tracking kind of how that evolves over time, which we can do with these kind of telescopes, hopefully, is what that metallicity is. We compare that with our models, and then we can start to say, well, that's a little bit lower than we expected, so actually there must have been more black holes than we thought, and we can start to adjust what's called our populations of the different sources.
You mentioned the possibility that sometimes there could be some fragmentation and get some smaller versions of sibling stars. I don't suppose you have any models that suggest what size they might be, how long they might last, and even perhaps possibly if the number around 15 billion.
Yes, why thank you. Why thank you for that well-talented question. So yeah, if when you're looking at how a gas cloud collapses and forms a star, you need extremely high resolution computer models. Now, it was the truth of the matter that until about 2015, we did not have the computing power to do anything but look at the central part of the cloud, where there was this massive star being formed, like 100 solar masses. And it kind of was literally the fact that we got an upgrade and we were able to get a bit more computing power. And we started noticing that in a lot of our simulations, we got these lower mass sibling stars, and that there was a certain number of 80% the mass of our sun. Now, if you can get stars smaller or as small as 80% the mass of our sun, they would survive 14 billion years. And this has created a whole branch of this idea, searching for kind of remnant stars like that might still be around us today. Like for me, it's like unearthing a Rosetta Stone. It's called stellar archaeology. So this is the whole field. It's a freaking awesome field that I kind of like, had I had my time again, maybe I'd have gone into that time. But it's so cool. And what they do is that they sift through billions of stars in our Milky Way, and they look at the metal content of them, and they try and figure out whether that metal content is low enough that it could be one of the very first stars. Now, it's not as simple as looking around and kind of being like, that star is completely metal free, as in like it's just hydrogen, helium. Oh, that's easy. It's a first star. Because when you've been hanging around a neighborhood that's really polluted for 14 billion years, you're going to have a ton of stuff on you. And we pick that up. And so it really is a case of looking at these tiny, well, not tiny, 80% mass of our sun stars, and trying to figure out whether, well, it is very low metallicity. Could it be camouflage? If it is, it might be a first star. So that's a whole different way of probing this time, which is just yeah, it's wonderful. They're getting really close. They found the first descendant. So this was, I think it was 2015 as well, actually. What they did was they found a star that was so low in metallicity that it could only have been formed from the products of one supernovae, as in there could only be one generation before it. So we found the first descendant. But oh dear God, but not quite the first star.